Welcome to Virtual Science. In the earlier class, we have discussed about the electric field, Coulomb's law, and so on. And now we are interested about the electric line of force. So, what is electric line of force? Electric line of force are imaginary lines or curves drawn from electrical charge, and its tangent at any point indicates the direction of its field. So, it is always directed from positive charge and terminate at negative charge. So, let's check one by one. Let me first inform you some of the features of the electric line of force. First of all, it generates from positive charge and terminates on negative charge. That means if we have a positive charge Q, suppose this one is my charge, and the electric field or the line of force for this charge is always outward direction, outward from this positive charge, which I have shown in this figure. Okay, and these are always perpendicular. And what happens for the negatively charged? For negatively charged, suppose minus q is my negative charge, and the line of force for this is towards the charge. That means the charge is here, the direction of this line of force is towards here, these are here. Okay, now if we have a positive charge 2q, then the electric line of force will be looks like this. For charge q, the line of force is denoted by A, and for charge 2q this is by C. So you can clearly observe from these two figures A and C that if the charge change, the line of force emitted or coming to the charge depending on the nature of the charge change. That means if charge decreases or increases, then the line of force also decreased or increased accordingly. Here the charge is twice than that of this one, that is why the line of force is twice than the first one. Second point, tangent of line of force indicates the direction of electric field at that point. Suppose this black one is my line of force, and I want to determine the direction of electric field at the point A, this point. So I am just drawing a tangent on this curve at from the point A. This is denoted by suppose AB. So the direction of electric field at the point A is always along AB. Third one, the electric line of force is always normal to the charged body. Suppose we have a charged body, and this is my charged body, and the line of force is always normal. That means normal to this surface. Another one is line of force never crosses each other. That means I have two line of force here and indicated by blue line and black line, and the features of the line of force is that the line of force never crosses each other. So what happens if they cross each other? Suppose I have two line of force indicated by black one and blue one, and they cross each other at point A, this one at this point. So at this point you can consider that there is two direction. That means I can draw two tangent from this point A towards curve black line or curve blue line, and so as a result there will be two direction and there will be two direction of electric field, but at a point there will be only one direction point, one direction of electric field, nothing more than that. So in this case there will be two direction of same electric field. At this point the electric field must be in one direction, but here this two direction, one by black line, black straight line, one by another one by blue straight line. That is why electric line of force never cross each other. And the last one, or the important one, is the line of force are imaginary, but the electric field directed by it is always real. Though line of force are imaginary, so you can consider that the direction obtained by the direction of electric field obtained by line of force is also imaginary, but not. The actual fact is electric field is always real. Now I am interested to sketch line of force for more than one charge. You have already observed that the line of force for a single charge or a single discrete charge, either it is positive or negative. So now I am considering that I have two charges, okay, placed in same electric field, and both are of same magnitude and both same nature. That means if one charge is q, another charge is also q. Both are, I am considering that both are positive one. So there must be a point inside this one, this is O1 and this is O2, inside O1 O2, where the electric field is 0, because this is positive charge, this is directed along this direction along O1A, and due to charge q, the electric field is q charge q at O2 is also positive. This is also directed at this one. So these are oppositely directed, field are oppositely directed, and as a result there must be a point where the electric field is 0. Let's say this is the point, this A is the point. As the charge, both charges are same, so the point where the electric field is 0 is the midpoint of the joining line between O1 and O2. So that means O1A equals to O2A equals to O1 O2 by 2. You can calculate it mathematically. Okay, this is your task. Do it yourself. So what will be the line of force for this case? Let me draw again. This one is my charge, this one is my another charge. Okay, this is q, this is also q. Sorry, what I've done. Okay, these are in same line, though this is not in same line, but actually this is in same line. So let me draw freshly. Okay, so there must be a point A where the electric field is 0. I am now sketching the electric field. Electric line of force. Electric line of force will go towards this direction, towards this direction, this direction. But when it comes to this direction, this will goes like this. It will bend, because the electric field at the point A is 0. That means there is nothing electric field, and so there will be no line of force. So this will be bent and looks like this. Here will be also bent. These are symmetrically. Maybe I am unable to draw this so clearly, but this is symmetrically. Okay, this one, and for this is this directed, this is this directed, and here it will come, and as both charges are same nature, they will repel, and at the point A or in this plane the electric field is 0. That is why it will similarly bend here. It will be bent here, and it looks like this one, looks like this one. Okay, looks like this one, but remember that no line of force will cross each other. This is a very good point. Now another question arises: what happens the two charges are not same. Okay, suppose there is a charge, sorry, there is another charge q1 and this is charge q2. Both are of same nature, that means either both are positive, and but the magnitude is not same, so the direction of electric field is along this one, and the direction of electric field due to charge q2 is this one. That means the electric field is also oppositely directed. That means there will be a point inside O1 O2 where the electric field is 0, but this is not the mid position of O1 O2 because the charge are not same. You can do this calculation yourself. Let me say that the charge q1 is greater than q2, so I think this may be the point towards the q2 where the electric field is 0, and I have to sketch the electric field again, electric line of force again. So my this one and this one are charge q1 q2. This will be similar like this one, nothing more than that. Just the midpoint where the electric field is 0 is towards shifted towards q2 as q1 is larger. Here one, so here will be this direction, this one, this one, this one, this one, this one. Okay, and the interestingly the point where the electric field is 0 is called the null point. So here A is the null point. At the null point electric field is 0, and so there will be no line of force. Now if the charge are negatively instead of positive one, then what happens? Same case for this one and also for this one, only for the negatively charged particles the line of force will be towards the charge. Here the line of force are away from the charge, the direction of the line of force are away from the charge because the charge is positive, and if the charge would negative, then the direction of line of force would be towards the charge. Now what happens if the charge are oppositely directed? Suppose I have a charge plus q here and another charge minus q here. So what will be the electric field in the interior? There will be no point where the electric field is 0 at the interior of these two charges, that means O1 and O2, because the direction of electric field at any point interior O1 O2 due to charge plus q is towards this one, and due to charge minus q is also towards this one. So there will be no null point in the interior between O1 and O2. Now let's draw the line of force for this case. This is my plus q, this is my minus q, this is line joining, and this is indicates one of the line of force because the it generates from positive charge and terminates on negative charge, nothing problem on it. What will be the other? This looks like this. Start from positive charge, terminates on negative charge. Similarly, starts on positive charge, terminates on negative charge. Positive charge. It's look like this. this one. So finally the direction of line of force for plus q and minus q is like this one. Now we will approach to the electric flux. So what is electric flux? The rate of flow of electric field through a given area is called electric flux. So the electric flux is proportional to the number of electric line of force passes through an imaginary surface. Mathematically, for an uniform electric field, suppose E is my electric field and there is a surface, this one, and this is denoted by the area of the surface is S. So the electric flux is indicates how many line of force passes through this one, and this is the direction of line electric field. So the flux indicates E dot S, where is the electric field uniformly distributed, and specific we can write this E into S, where electric field is normally directed towards the surface. But if electric field is not normal to the surface but making an angle theta, suppose this is my surface and the direction of electric field looks like this. So what happened then? Then I have to first consider the normal of the surface. Normal of the surface is this. This is indicated by theta. So in this case, the electric field, this is electric field, this is the normal of the surface. So flux phi equals to E dot S, that means ES cos theta. Now for non-uniform electric field, we can find the flux, electric flux phi, by integrating this E dot ds. That means if we integrate surface, if we perform surface integration over electric field, we can get the electric flux. Okay, this suggests that flux indicates total charge present inside the surface. For the field lines that originates on a positive charge must either pass out through the surface or else terminate on negative charge inside the surface. On the other hand, the charge outside the surface will contribute nothing to the total flux. Suppose I have a surface like this one and I have a charge inside the surface, either positive or negative. If the charge is positive, the electric field, line of force will emits outward, or if the charge is negative, it's towards the charge. But if the charge is outside the surface, suppose this one is my charge and this is my surface, this black one is my surface. So what happens then? Then the number of, for I am considering for positive charge, so here the line of force coming inside the surface and going outside the surface will be same, and there will be nothing lost in the surface, and that is why there is no effect of charge outside the surface for the calculation of electric flux. This is most important factor, and this is the basic essence of the Gauss law. That means if we have a charge, either positive charge or negative charge, at outside the surface, then there will be no effect of this charge for the calculation of electric field, or it will do nothing. This is basic essence of Gauss law. And now Let's calculate the Gauss theorem mathematically. Let's consider a point charge at origin. Okay. Now the flux E, the flux of electric field through the sphere of radius r. Suppose I am considering a sphere here, and this is of radius r. So the flux is integration E dot ds, and the electric field at a point r due to point charge q is q by 4 pi epsilon naught r square, and in spherical polar coordinate system ds indicates r square sine theta d theta d phi, and we have to integrate over theta and phi. Theta varies from 0 to pi and phi varies from 0 to 2 pi. So we can put theta varies from 0 to pi and phi varies from 0 to 2 pi as for spherical polar coordinate system case. So this gives us q by epsilon naught. So this is quantitative form of Gauss law. That means electric flux phi equals to q by epsilon naught. That means more generally we can write that phi equals to E dot ds equals to q by epsilon naught. According to this law, total electric flux is the total charge enclosed by the surface divided by the permittivity of free space. Here the charge q is the charge enclosed by the Gaussian surface, because I have considered here that a sphere of radius r is the Gaussian surface and the charge in the interior of the surface. So I can write it that E enclosed. So the charge which is only inside the Gauss surface is effective for the calculation of the Gauss law and for the application of the Gauss law to calculate the electric field. So by this theorem we can calculate the electric field easily, but the main point is we have to consider only the charge which is inside the Gaussian surface. The charge which is outside the Gaussian surface is not effective for the calculation of electric field by using this law. This is very much important. And this equation is in integral form, so it can be write down in also differential form. Now for this conversion we have to use vectors method. Suppose we have a vector a, and according to Gauss divergence theorem, surface integration of a dot ds equals to volume integration of divergence of a dv. This is the basic Gauss divergence theorem. We can put it here for the left side also, and the total charge can also be written as charge density multiplied by volume, okay, multiplied by dv. If we consider a small elementary volume dv and the charge is uniformly distributed, so the volume charge density is rho equals to charge divided by total volume, and q can be written by this. So putting these into the equation, we can get divergence of a dot dv equals to rho is constant, so I can put it at outside dv. So finally what we can get, divergence of E equals to rho by epsilon naught. This is divided by, this is the divergent form of Gauss theorem, and this is the integral form of Gauss theorem. Now I have to interpret this equation. Now divergence of E equals to rho by epsilon naught. This is the mathematical divergent form of Gaussian theorem, Gauss law. But what is the physical significance of divergence? Divergence means how much a quantity is diverged. Suppose I have I have some liquid flowing through a surface, um, closed surface. Some liquid enter into the surface and some just emerge to the surface. So the lodge inside the closed body is the divergence. For this case also, the line of force which is lodged inside the surface, Gaussian surface, is the indication of this divergence of E. If the what I have said earlier is exactly matched with this one. If the charge is outside the Gaussian surface, then the total divergence is zero, because what is entering is same amount of emerging through the surface. That is why divergence of E equals to 0. And if the charge is interior of the Gaussian surface, then there will be a non-zero value. So let me finish here, and I will discuss in the next class that different types of Gaussian surface and application of Gauss law to determine electric field for different cases. More will be discussed in the next class. Please subscribe our channel and comment in the comment box, and for further query please mail us at farsighteach@gmail.com. Thank you.